video might not be as good as I have all my family here. So if you hear some random noises, well, that's that. All right, number 5 isn't too bad, but it introduces a new concept to us, which is called partial pressure. So it gives you 20 grams of 3 different gases. It gives you a volume and a temperature, and it wants the partial pressure of each gas. So first, just to talk about what partial pressure is, I went ahead and wrote this out. Partial pressure, qualitatively, is the pressure of one part of a mixture of gas. So if you have 3 different gases, the partial pressure would be the pressure that one is putting towards the total, or the second one is putting towards the total, or the third one. All right? It's not too bad, and the math really isn't that bad either. It just takes a lot of steps. Partial pressure quantitatively is equal to this x, it's really chi, but whatever. I don't know if we've done that in this class before, but when it's written a little bit weird, x means the mole ratio. And we'll get there. So we take the mole ratio and we just multiply it by the total pressure. So the mole ratio is this equation. It's moles of A over the total moles. And once we find this ratio, then we can just multiply it by the total pressure, and we can find the partial pressure of each thing. Now to find pressure in this problem, we just use Pivnert like we've been doing all day. Alright, so the first step that we need to do, and I've already done it, will be to find the mole ratio of each thing. So if I come back to this page, I did most of this math already. So the mole ratio, once again, it's the moles of A over moles total. So the first thing I did was take the 20 grams of water vapor and divide it by the molar mass of water, and that gives me moles of H2O. Then 20 grams divided by the molar mass of carbon dioxide, and I get 0.455. All right, and then 20 grams for nitrogen, and remember it's diatomic, so that's why it's 28 grams and not just 14, and it's 0.714. All right, so that tells me the moles of each thing, but to find the ratio, I now have to divide all these numbers by the total, which I don't have yet. Moles, which is just adding all 3 of them together. I'll pause this. So what I went ahead and did is I added these 3 numbers to find the total number of moles, and it's this 2.28, and that's the denominator each time in my mole ratio calculations. So then I already had the numerator. So moles of A in this problem is moles of H2O divided by total, and then CO2 divided by total, and then N2 divided by total. And I got these 3 values, all right, and those are the mole ratios, or the little goofy looking X. All right, now what we need to do is now find the total pressure. And PV equals nRT, we rearrange that. P is equal to nRT over V. Now I'm running low on space, but I'm going to cram all this in. Hopefully it looks okay. So the pressure, I need the total moles, which was this 2.28 that I already calculated. So 2.28 times R. This is going to get ugly. Let me put it right here. 2.28 times R, which is 0.82 or 0.821, times temperature is already in Kelvin. That's 398, and I divide that by the volume, which is 2. I'll plug that in. My calculator, I get 37.25 is my pressure. So now I'm ready to plug all these in. I take the mole ratio and I multiply it each time by this answer, 37.25. And I'm going to repeat that 3 times. I plug these in each time. Mole ratio times total pressure, mole ratio times total pressure, mole ratio total pressure, I'm good to go. So in this container, 18.14 atm of pressure is coming from water, 7.45 atm is coming from CO2, and 11.66 atm are coming from N2. So that's partial pressure problems. Hopefully that was a fairly understandable problem.